Hello, everybody. Today we will be solving problem 7 from the Algebra and Number Theory round of HMMT 2021. The problem reads, suppose that x, y, and z are complex numbers of equal magnitude that satisfy x plus y plus z is equal to negative root 3 over 2 minus I root 5, and x, y, z is equal to square root of 3 plus I root 5. If x is x1 plus ix2, y is y1 plus I y2, and z is z1 plus I z2 for real x1, x2, y1, y2, z1, and z2, then the quantity x1, x2 plus y1, y2 plus z1, z2 squared can be written as a over b for relatively prime positive integers a and b. Compute 100a plus b. Okay, so before I go and dive into the nitty-gritties of this problem, I'm going to introduce a few properties of complex numbers. The first is, let's say you have a complex number, we'll call it k, and k is equal to a plus bi. Then we have the magnitude of k. That's the distance from k to 0. It's actually going to be equal to square root of a squared plus b squared. Right? We're also given, well, we're not given, but we're going to use this fact that if we have the conjugate of k, which I'll denote as k with a bar over it, the conjugate of k, which is a minus bi, then we can realize that k times the conjugate of k is equal to, well, a squared minus 2abi plus 2abi minus b squared I squared. And this is going to be equal to a squared plus b squared, which is going to be equal to the magnitude of k squared. So that's going to be useful. One other thing we have is if we have some numbers m plus n plus p squared, we can expand this out to be m squared plus n squared plus p squared plus 2 mnp, nope, 2 times mn plus np plus mp. We're also going to use this fact. All right. So now for the real math, we're going to start with this expression x1, x2 plus y1, y2 plus z1, z2 squared, and we're going to work backward, right? What we can do is we can take x squared and we can write it as x1 plus ix2 squared. And we can write this as, if we expand out, we get x1 squared minus x2 squared plus 2x1 x2i. And you see this last term, it looks kind of familiar, and we can realize it's because x1, x2 is actually a term in what we want to find. This expression is squared, right? We can write y squared similarly, y1 squared minus y2 squared plus 2y1 y2i, and z squared is z1 squared minus z2 squared plus 2z1 z2. Right, now what we're going to do is we're going to take x squared plus y squared plus z squared. But we're just going to take its imaginary part. So I'm going to write im of this thing, just that's basically the imaginary part of this sum, and we're actually going to get 2 times x1 x2 plus y1 y2 plus z1 z2. And we want the thing in this parentheses squared, right? So I'm actually going to write over here what we want, which is this x1 x2 plus y1 y2 plus z1 z2 squared term is half of the imaginary part of x squared plus y squared plus z squared. All of that squared. All right. So now I'm going to go ahead and clear some of this stuff because, well, it's going to get pretty messy. Okay, so first of all, what do we know? We know that from this identity over here, x squared plus y squared plus z squared equals x plus y plus z squared minus 2 times the quantity xy plus xz plus yz, right? Now we have a bunch of information. We know what x plus y plus z is, and it's going to be pretty easy for us to figure out what this is, right? So first of all, x plus y plus z is this thing. We'll plug that in a bit later. But now what we can realize is that this second term, where we have xy plus yz plus xz, it's going to be equal to x, y, z over z plus x, y, z over y plus x, y, z over x. You can realize that this is x, y, z times the sum of the reciprocals of x, y, and z. And that's where this other formula comes in, right? Because we have 1 over x is going to be equal to, well, we're going to write this as x, y, z. Well, 1 over x is going to be equal to complex conjugate of x over the magnitude of x squared. And then this 1 over y term is going to be the complex conjugate of y over the magnitude of y squared. And then this 1 over z term is going to be the complex conjugate of z over magnitude of z squared. Right? But we are given x, y, and z are complex numbers of equal magnitude. Equal magnitude. What's that going to mean? It's going to mean that the magnitude of x, y, and z are all equal. So this is going to be equal to x, y, z over magnitude of x squared times the sum of the complex conjugates right? What's the complex conjugate? Sum of the complex conjugates, that's going to be x1 plus y1 plus z1 minus I times x2 plus y2 plus z2. Right? Now we need a few things. We're going to need, first of all, we're going to need magnitude of x squared. But then first we can take a look at this equation. XYZ is square root of 3 plus I square root of 5. And then we have the magnitude of that is square root of 3 squared is 3 plus the square root of 5 squared is 5, which is square root of 8. But magnitude of XYZ is the magnitude of x times the magnitude of y times the magnitude of z. Right? That's a property of complex number magnitudes. But since all of them are actually equal to each other, this is going to be equal to the magnitude of x cubed, which means the cube root of this term is going to be the magnitude of x, which we can realize is square root of 2. So the magnitude of x squared is 2. So I'm going to actually go ahead and replace this with a 2 here. Now we need this value. But the complex conjugate of this plus the complex conjugate of that plus the complex conjugate of that It's going to be equal to the complex conjugate of this whole thing over here, x plus y plus z. This conjugate is going to be negative root 3 over 2 plus I root 5. So I might as well clear up some more space. And we get x plus y plus z. The sum of these complex conjugates is the complex conjugate of this, which is negative root 3 over 2 plus I square root of 5. Right? So x, y, z over 2 times this is going to be 1/2 times root 3 plus I root 5 times negative root 3 over 2 plus I root 5. You can evaluate this and you get 1/2 of negative 3 over 2 plus I times, what is it, root 15 over 2. And then minus 5. All right, so that's xy plus yz plus xz. And we can plug that back into our formula. And what do we get? We would get, well, 2 times that is just 2 times 1/2 times negative root 3 over 2 plus I root 15 over 2 minus 5. So we have the whole thing is equal to x plus y plus z squared minus 2 times this whole quantity, which is going to be negative 13 over 2 plus I root 15 over 2. And then x plus y plus z is going to be this thing. So the square of that is going to be, well, we have squared minus negative 13 over 2 plus I root 15 over 2. We can evaluate this square out and we get, well, root 3 over 2 squared minus I over 5 squared. We get 3/2 minus 5 plus I square root of 15. And then minus this whole thing. So finally, we get x squared plus y squared plus z squared is going to be equal to 3 plus I root 15 over 2. So the imaginary part of this is going to be root 15 over 2. And we want, remember, we want this thing. So we want 1/2 times this imaginary part all squared. And this would be 15 over 16. And since 15 and 16 are relatively prime, 100a plus b is just 1516. Thanks for watching, and I will see you next time.